Hey everyone. Okay, so we're back to stellar evolution, stars and stellar evolution, but I wanted to show you something. This was taken in March of 2006, and this is called the Composite Crab Nebula. And guys, this is where stars are born. Okay, they're born in this type of stellar dust, and there's so much energy going on here. It ignites new stars, and we get the birth of a star in this area. So I just wanted to show you this. This is from Astronomy Picture of the Day, which I do have on our website, our class webpage. At the bottom, if you go down, you will see, I believe, the Astronomy Picture of the Day is there. If not, I will put it up. There's some really cool stuff there. If you type it in, you can actually get the astronomy picture of the day emailed to you every day, and you can see what's happening. This is called the crab. Inside, you have the crab pulsar, and it has a description down at the bottom. Okay, so I wanted to show you the HR diagram that appears in your Earth Science reference guide. Just make sure that you understand how to read this, and you will see in the rest of the podcast how to read this. But very quickly, your main sequences here. You have your giants, your supergiants, your white dwarfs down here. Uh, Notice massive stars, small stars, the color of your stars, which match up with your temperature, which we'll go through later on. Your luminosity here, okay? So the sun is right here. If I go down, I see that it's a yellow star. Okay, its spectral class is the G, which we'll go through, and then it gives you the temperature right here. So understand and know that questions that will be on your next test will probably coincide with this reference table. Okay? So I just wanted to go over that. Now we finished stellar magnitudes, star magnitude, and you should be completing your lab with the magnitude. Hopefully you get a nice, beautiful night with all those stars out. Guys, use your app, your phone app if you have to with that lab, okay? But it is not a hard lab, and I'll explain it to you in the class. Okay, so stars' colors depend on their surface temperature. So, for example, if we look here, okay, you have intensity on your y-axis and wavelength. So again, this is why we use light, because light is part of this whole subject, this whole area. So if I have a color of the star that has a 3,000 Kelvin, K is for Kelvin, guys. You guys have to know these temperatures. Okay, Kelvin is what we're going to be measuring. In astronomy, that's pretty much all we measure. Okay, so you have Kelvin. So if I have, it's going to emit more red light than blue light. Okay, it's right here. So here's your red. So it's going to emit more red. Why? Because that is where it is not emitting a lot of energy when it is the red wavelength. Now, if I go up to like 550 Kelvin, which emits equal amounts of visible wavelengths, so it's kind of a yellow and white light, so right about here, okay? And then if it is above 10,000 degrees Kelvin, it's going to emit blue light. So what am I saying? Hot stars are going to emit, and here we right here, temperatures above 30,000 Kelvin. And it's going to be on the short wavelength, the blue wavelength. Cool stars are going to emit less than 3,000, and they're going to be on the red part of the spectrum. So our spectral classes, what we call our spectral classes, they are figured out through temperature. And how they're figured out through temperature is through surface temperature and color. So when we look at our spectral classes of different stars and the apparent colors, this is what you're going to see. Our sun, yellow, white, because its surface temperature is about 5,800. Okay? Uh, Betelgeuse, 3,500, so it's in the red area. Okay, Bellatrix 21,500, it's in the blue area. It's massive too. Bellatrix is, I believe, a super blue giant, and we'll talk about that in a little while. Okay, so our spectral classes, when we look at them, this is how we classify them: O, B, A, F, G. They were based on their spectral lines. So here is our spectral classes. Notice, and this is the most important one that you need to know, is the sun is a spectral class of yellow. Very important. You need to know that one. Okay, so how do we classify stars? We use what we call the HR diagram. You have a lab in which you're going to use, and you're going to actually go through, walk yourself through, and you're actually going to build the HR diagram and know how scientists develop this diagram. It's very important. I mean, it's not hard to understand. You have your, I apologize. You have your luminosity on one side, which is your brightness, and your temperature on the other side, your absolute magnitude, which is, remember, absolutely. We know this is the brightness of the star. Your luminosity is also the brightness. There's a relationship between your spectral class and how bright the star is. Okay, this right here is your, what we call the red curve is the main sequence stars, your normal star. Well, that's the path of stars in their evolutionary path, okay? So when we're looking at this, you're pretty much plotting, you're graphing what your stars are. Our sun is right here in the middle of its evolutionary path. And what's going to happen is certain stars, depending on their mass, is going to evolve up this and will go this way, or they're going to go, if they're small stars, they might go this way. Okay, large stars are going to go to the supergiant areas. Notice right here, your surface temperature, depending on your color again, is going to be your surface temperature, right? So the HR diagram pretty much classifies all your stars, and they classify them on the main sequence, which is the main evolutionary path of the star. Your dim stars, like your white dwarfs, are down here, and your much brighter stars are up here, which are usually your supergiants. Arcturus is right here, and you can see some of these supergiants at night. You see a chance. So now we talk about stellar evolution. We'll get into stellar evolution. And stellar evolution, the star starts off, we have two opposing forces going on inside the star. We have gravity pushing in and then thermal pressure pushing out, or thermal and nuclear energy, which expands it. So when a star is born, it's born in interstellar clouds, like we just talked about. I talked about that when I showed you the Crab Nebula cloud. The gravity contracts the cloud and the temperature rises, and then we get this red light, and we get the beginnings of what we call a baby star, which is a protostar. As the protostar goes through, okay, we're going to get gravitational contraction, and we're going to begin the fusion process. Once the fusion process starts, which we call hydrogen burning, which is hydrogen becoming helium, then we begin to get, we call it a star. And that's when the star becomes a main sequence star. Now, what you are going to do in one of your labs is you're going to use this to help you out. This is a poster that I will hang up in class, and you will have the opportunity where you can go and you can actually look at this in class if you need to, but you will have this available. It will be your lab that you are going to do, which is part of the Chandra website, and I thought we had it open, but I guess we don't. Okay, so what's going to happen is you will have two parts to this lab. The one part is you're going to use the Chandra website. Okay, so if you open, that'll open up for you, and it'll go to the Chandra website, and you're going to actually go through the stellar evolution poster, which I am showing you here. Okay, so I'm going to explain that this poster, if you notice, the mass is on your Y, time is here on your X. Each of these is a protostar that has a certain type of mass. The large, very massive protostars that turn into our blue supergiants, they become massive black holes and then supernova. Pretty cool, right? And on the back of the poster, it's going to give you examples of each of these. So it's examples that Chandra actually saw with the help of other telescopes also. Now our sun, notice our sun's evolutionary path. So we become a protostar, and notice our sun is not too large but not too small. It's right kind of average. Our sun, right, it develops, forms, and then what happens in 15 billion years, our sun's going to become a red giant. No fears. We'll probably all hopefully be evolved and now off Earth and somewhere else. But anyway, it's a red giant. Once the red giant begins to collapse and uses all its fuel, it's going to become a planetary nebula. Now, there's two things this can happen. The sun can become a white dwarf and then end, or it could eventually supernova into a type 1 supernova. So that's our sun's path. To a red giant, it's next. Notice the path of the larger stars. They end pretty violently, don't they? You have a type 2 supernova and then a black hole here for this guy, which is a blue supergiant. So you have your two blue supergiants. Here's your other blue supergiant that can turn into a red giant and then back to a blue giant and then could go back to a type 2 supernova, and this guy's got a really big big evolutionary path. Then you look down here at the brown dwarf and they pretty much stay brown dwarf. That's it. No change, nothing. So understand and know that this is what you're going to be doing in this lab. You're also going to use these photos and you're going to sequence them. So they're going to be very similar to this, and they're going to be based on Chandra and what it's seen. And when you do this lab, one of the things I want to point out to you is you can take those pictures and cut and paste them and put them in a PowerPoint so that you could actually write your descriptions and put them in order. Now, you can use this as your templates. Now, if you want to use these just as your templates and do a paper lab, you're going to have to copy more of these sheets because you're going to need more than one page to finish that. Okay, so that's your Internet and Stellar Evolutionary Lab. This is your evolutionary path. I'm going a little over here, so we're going to make this a 15-minute, a little bit longer. Your evolutionary path, okay, once you have your final stages, it will all depend on your mass, and you saw that. And then I go through in the notes and I give you a couple of the gravitational pull in the picture here of a low mass star and what happens. Low mass star goes from nebula, protostar, main sequence, and then a white dwarf. That's low mass. This, it might be yellow, but this is not the sun. Okay, our sun is a middle age star. It's an average star. It's a middle mass. Okay, I will stop here because we're going to have to continue on another third part.